30-3, let us continue with geometric shapes. You know, I always got a kick out of this that we do geometric shapes. And the shapes, man, don't babies get shapes as like gifts when they're like 1 and 2 to learn shapes? They do, but we're talking a little bit more academic math with them. Hopefully the triangle stuff wasn't too bad. Today we're going to talk quadrilaterals. Quadrilaterals, of course, quads meaning 4. If you have quad of something, you have 4 of them. So we are talking about anything that is 4-sided. Now, 4-sided, there's all kinds of possibilities. We're going to talk about the characteristics of all the different types. Quadrilaterals, 4-sided. If you take a look at page 10 has that diagram on there. I want to jot some information. It wasn't going to be easy to jot it on my smartboard, so I'm not going to put the entire chart up there. I'm just going to kind of work as I go through, and you can fill in the charts in your booklet. So let's talk the different quadrilaterals. Well, we're first of all starting off simply with quadrilaterals. Now, quadrilaterals, they sort of have generic types of quadrilaterals that can then be broken off into more specific types. One general type of a quadrilateral is a parallelogram. Now, parallelogram tends to be 4 sides. It's like a rectangle that's been blown over. We have opposite sides are parallel. 2 arrows top and bottom, single arrows on the sides, because those are parallel. Now, the other part of a parallelogram that's important to understand is not only are opposite sides parallel, but opposite angles are the same. And I showed the other day that different ways to show similarity for angles. The 2 angles that are diagonal and the other 2 angles that are diagonal are congruent to each other, the same. So in that case, we can see, and the other thing that's important to understand is you have an acute angle on those 2, so it's obviously not going to be the same as the obtuse angles. But the obtuse angles will be the same, the acute angles will be the same. That's, in general, what a parallelogram is. However, we can become more specific with our parallelograms because a parallelogram can be branched off to more specific shapes. Because what's important about a parallelogram? Opposite sides parallel, and besides that, we have opposite angles are equal or congruent. So that's important. Well, there are a couple of special parallelograms, and one of those is the fact that we have a rectangle. And a rectangle is a parallelogram because a rectangle has opposite sides parallel, like the parallelogram, obviously. However, what makes parallelograms special is, hopefully most of you are aware, when we look at opposite sides, well, what makes the rectangle a unique parallelogram is all sides are 90 degrees. That's not new information to us, but a parallelogram, opposite sides are parallel, opposite angles are congruent, which is what we have in a rectangle. But the other one that's kind of unique with that is what we have, sorry that you can put if you don't know, that's a rectangle. The other one is, I'm not sure how well I can draw it. You got to just, this is not a good drawing. But this is why, again, we use symbols if we can't draw it well. So what we have here is a special parallelogram. Again, sides up opposite across from each other are parallel, but in this case, what else is important is this particular parallelogram, all the sides are the same. In a rectangle, we have double ticks on that side, single ticks on the other sides, because not only does a rectangle have equal sides, not only does a parallelogram have equal sides across from it as well. But in this case, we have a parallelogram. Again, opposite angles are the same, always. But when all the sides are a parallelogram, so we have opposite sides are parallel, Opposite angles are congruent, but when all sides are equal, we have what's called a rhombus. So special parallelograms. And we can now bring the idea of a rectangle and a rhombus together to a square. Why is a square the most unique parallelogram, you could argue? Because opposite sides are parallel. We know that. Opposite angles aren't only not just the same, but they're 90 degrees. And all sides are the same. So it has rectangle features and the rhombus feature of congruent sides, and that's why a square is so unique. It has all these little traits of a parallelogram, but then the special traits of a rectangle and a rhombus. So there you go. Now the other type of quadrilateral that is a little bit more unique is a trapezoid. Now a trapezoid you've seen before, but what makes a trapezoid a trapezoid? Well, there's a generic trapezoid and then we can have some unique features about it. Well, a trapezoid, 4 sides, but a trapezoid has one set of parallel sides. So we can see, even though it's not drawn perfect, we could put our symbols in and opposite sides are parallel. You'll note that the opposite sides in this case, both of these, a trapezoid can have all different side lengths, 4 different sides. The key part for a trapezoid, one set of parallel sides. 4-sided, one set of parallel. That's all you need in order to have a trapezoid. Well, the trapezoid, though, can be specific trapezoids. The first one, if you take a look at the way it's drawn, is we're going to add some symbols to it. Trapezoid, because we have a set of parallel sides. But my drawing's not perfect, I know. But from the drawing that's there, what do we see? We see that we have ticks. Well, there's no way the top and the bottom are going to be ticked because it's trapezoid with the parallel sides. But these sides across from each other, this is what we call an isosceles trapezoid, because there's a set of congruent sides. Isosceles trapezoid, one set of congruent sides. Just like an isosceles triangle has a set of congruent sides. An isosceles trapezoid also has a set of congruent sides. But what's important is when you have an isosceles with a set of congruent sides, is you have 2 pairs of congruent angles as well. So when we take a look at this, we see that we have, if it was drawn like the one in your diagram, when you have an isosceles trapezoid, down at the bottom here, we have 2 acute angles, and they are the same because it's an isosceles. But with that being said, we also have up top here 2 obtuse angles, and those angles, I'll mark with check marks, are also congruent. So an isosceles trapezoid, one set of congruent sides, which makes it special. Still have the parallel sides, but one set of equal sides, which then gives us these congruent angles. And that little bit of knowledge will help us when we look at all these shapes. The second trapezoid is a special trapezoid because you can see that it's been drawn like this, and it has the boxes in there. We still have one set of parallel sides, which makes it a trapezoid. But this case, our other 2 sides, they're not the same, but one of them is made up with right angles. So these right angles make it a right trapezoid. So that's a right trapezoid. So quadrilaterals have very general names for certain types of quadrilaterals, but we can branch off to more and more specific ones. From there, what we're missing with our quadrilaterals is a special one referred to as a kite. So we have a kite in this case. Now a kite has two sets of congruent, not parallel, but congruent sides. So two sides are the same and two other sides are the same length. But what that also gives us is these two angles across from each other are the same. One set of congruent angles in a kite. And the last one for a kite that makes it special is when you have diagonals, and diagonals join opposite angles. The diagonals always meet at 90 degrees. So that's what makes the different quadrilaterals. And the little bit down in the bottom corner, triangle, angles equal 180 degrees. Well, in any quadrilateral, any type of quadrilateral, the angles equal 360 degrees. And that little bit of information will help us as we look at examples. So, characteristics. You know what a quadrilateral is, it's four-sided. But it's not just about, four-sided. Every type of quadrilateral has some uniqueness to it. So let's turn to page 11 and look at some of the examples and what we can do with that. So if we take a look at the first one says, find the length of AC, find the size of angle A, angle B, and what type of quadrilateral is it? Well, if we take a look, you can look back at the information, but as soon as I have, well, what does this look like? And what it looks like is what it is. Well, we pretty safe to assume that those are parallel because these angles are the same. So 60 and 60 in a trapezoid. If I have angles that are the same in a trapezoid, it has to be an isosceles trapezoid. There you go. Because angles are the same. If I have a trapezoid that doesn't have the same sized angles, there's my parallel side, but my angles, none of the angles are the same, well, it's just a trapezoid. But when angles are the same, it's an isosceles trapezoid. So, what's the side length of AC? Well, AC, if it's isosceles, because the angles are the same, that means my sides have to be the same. So AC is 4 centimeters. Angle A and angle B. Well, angle A and angle B, an isosceles trapezoid has two sets of equal angles. We just talked about it. So angle A and angle B are actually equal. But how do we figure that out? Well, we know that a trapezoid has 360 degrees total. So if I subtract from my 360 the two angles that I know, subtract 60 and subtract 60, we get 240 degrees. But those aren't 240 degree angles because that 240 needs to be split between the two angles. So we have a total of 360. Take away the two angles we know, we're left with 240 degrees, but that needs to be split between A and B. So we split it in half, and angle A and B are each 120 degrees. So all these characteristics tie together. Well, here we have a kite for the second one. And the kite tells us two sets of equivalent sides. We can see that. 3 and 3, it's a kite, there you go. WX, well, that's another congruent side, so this has to be 2 centimeters. XYZ tells us the angle from, when it's written with 3, we want to go from X to Y to Z. So that angle. Well, how big is that angle? those two opposite angles are the same, 101 degrees. And this second part asks WXY and YZW. Oops, Y to Z to W. They want to know what's the total of these two angles. Well, it doesn't ask for them individually, just wants the total of them. Well, what do we know about a quadrilateral? 360 degrees. We know two of the angles are 101. So if I take 101 degrees from 360 twice, we get left with 158 degrees. So we know that these two angles together will be 158 degrees. These two angles are not equal. It's just the ones that are beside each other that are equal, the green ones that I identified. These other two, total 158 degrees together, we don't know what they are individually. There's just no way to know. Page 11, the last one on this page. What are our angle sizes? Well, this one's going to be pretty quick. We see the double ticks, isosceles trapezoid. So that's 118 degrees as well. Isosceles means S and R are equal. Angle S equals angle R. So we take our 360 degrees for the trapezoid, subtract the two 118 degrees from each, and we're left with 124 degrees. But S and R we said are equal, so I divide those by 2, and we get 62 degrees for each because of that 360 and knowing the angles are the same because it's an isosceles trapezoid. Page 12, two quick ones here. This first one up top's a little goofy, a little hard to see. But if you read the example, you can pause the video, read it, and then come back. What we've created here, and my diagram's not perfect, but if everything is parallel, we end up with a trapezoid that's isosceles. These would be the same if it was drawn perfect. And we know that this one here is 38, and so that's going to be 38 everywhere. That's 38 degrees. And it's, like I said, an isosceles trapezoid. So if this is 38 here, well, its partner, angle 4, is also 38 degrees because this is an isosceles trapezoid. Angle 1 is the same as angle 4, and because it's isosceles, angle 3 is the same as angle 2. How do we figure that out? Well, 360 degrees minus the 38 degrees twice. What does that leave us with? That leaves us with 284. Split that between the two angles, 142 degrees each. So there's the measure of all those angles. A little bit of a different question, but as soon as I'm hoping I say the word isosceles trapezoid, wait a sec, here we go. Angles are the same in an isosceles trapezoid. Then we can use the 360 rule. The last one is going to be a little bit more involved, and we'll talk about why. We need the perimeter first. Wow, we just want the perimeter of the parallelogram. So you got to be careful. This little triangle on the outside is going to help us in a bit, but we need the parallelogram. Parallelogram, 8. So that's 8 as well. But perimeter is always a total of all the sides. So we have 8 plus 8 plus something plus something. We need to know what these somethings are. Well, does anyone know what to do to get those somethings? Well, this little triangle here is really helpful because what kind of triangle do we have? Well, when we take a look at that, we end up with a right triangle. We can see a right triangle. Well, how can I figure out this unknown side length? Well, a right triangle, we can use Pythagoras. So this blue triangle now, we're trying to find the hypotenuse. So a squared plus b squared will equal our unknown hypotenuse squared. 9 plus 4 is equal to c squared because we're just using Pythagoras here. 9 plus 4 is 13, but we always finish Pythagoras by square rooting. Square root 13, and we get a value of 3.6. So we know that we have a 3.6 side here, and because it's a parallelogram, it's a 3.6 side there. So we're adding 3.6 as well. Distance around 8 plus 8 plus 3.6 plus 3.6. So we need to use all the information, including this extra triangle that helps us. Total perimeter is 23.2 centimeters. There you go. Now we want to know the size of angle ADC and DCB. I'm just going to erase some of my drawing on here to help us see. So we said that this was 8 up here, and we have 3.6 for these pieces. We want to know ADC from A to D to C. We want to know how big that angle is. And from D to C to B, we want to know how big that angle is. Well, there's no information in that parallelogram, but we have this triangle. And when we have a right triangle, we can calculate angles. So let's calculate this angle here. So let's use right triangle, calculate an angle size. Let's use trigonometry. So here we go. What do we know? We know this is 2. We know this is 3. We're trying to find angle D. Angle D is our reference angle. So opposite is 3. Adjacent is 2. Hypotenuse isn't known. So we're not going to use hypotenuse. We want angle D. Remember, opposite adjacent is tangent. So we're going to do tangent of angle D. Opposite 3 over adjacent 2. How do I get my angle? I second function the 3 halves. Second tan, so we get our inverse tan of 3 over 2. So angle D works out to be 56 degrees. So we have 56 degrees here. Now, those aren't the angles we were asked for. We were asked for this angle, and we were asked for this angle. Well, very quickly, here we go. We have a straight line here. So this angle ADC would be 180 degrees for a straight line. Subtract the 56 to leave us with the angle that we want. And that works out to be 124 degrees. And now we want angle DCB, which is this angle here. Well, remember, what do we know? In a parallelogram, we have 124. We have 124 there because they have to be the same. And then parallelogram opposites will also be the same. So we know it's 360 for the entire parallelogram. Subtract the two 124 degree angles, and that's going to leave us with 112 degrees, but it needs to be split between the two angles. So we have 56 degrees for each angle. And you can do a quick check. All of these angles added together, 360 degrees. So lots of little things to think about. Quadrilaterals, all that information we started with are puzzle pieces to help us put the puzzle together. Assignment booklet, page 13, 14, 15. remember, I have the key. My second booklet is posted on the Google Class to give you answers, to help you. If that doesn't make sense, reach out and we can talk. Have fun with it.